Well, in this video, let us try to understand what do you mean by Wheatstone bridges. So first, Wheatstone is the name of a scientist. On his name, it's being called as a Wheatstone bridge. It's a combination of 4 resistors where the Kirchhoff's laws are applied and the simplified result is shown for you. You know the Kirchhoff's current law, the algebraic sum of currents at any junction equal to 0. You know the Kirchhoff's voltage law, the algebraic sum of voltages in a closed circuit equal to 0. But applying Kirchhoff law every time for any circuit takes a lot of process to happen. So one predefined circuit is already drawn for you, and that is called something like a Wheatstone bridge. They are arranged like a bridge and there are 4 resistors into it. Let me name that resistors as P, Q, R and S. In this bridge there are obviously 4 junctions, nodes, like I have pointed out. So when these 4 resistors are connected this way under a particular condition, what is the ratio of resistances is the formula of that Wheatstone bridge. So between 2 junctions, a galvanometer is connected in the Wheatstone bridge, and between the other 2 junctions a battery of EMF E is connected, without which current cannot flow in the circuit. So this is an EMF E. Now before going to talk anything else, let us see how does the current distribution happens in the circuit. Current always starts from the positive plate of the battery, that is this way. After reaching this junction, the current gets distributed. Let the current through P equal to I1, current to the other resistance equal to I2. So obviously applying Kirchhoff's first law at this junction, currents coming towards the junction is I, currents leaving the junction is I1 and I2. So according to Kirchhoff's junction law or current law, I equal to I1 plus I2. Well, let us see how the current progresses further. I1 after reaching here will split between these two. Let some current passes to the galvanometer Ig. Remaining current of I1 passes to the resistance Q. So how much is that? Out of I1, Ig has passed here. Then I1 minus Ig passes to the resistance Q. This I2 will further progress towards this junction. Ig also is progressing that junction. So the currents coming towards that junction is I2 and Ig. So the currents leaving the junction is also equal to I2 plus Ig. So if you consider this junction, now look at the currents reaching this junction. I1 minus Ig is reaching from here. I2 plus Ig is reaching from this place. So what's the total current? I1 minus Ig plus I2 plus Ig is the sum of the currents coming towards the junction, is the sum of the currents leaving the junction. Therefore Ig and Ig will cancel. It will become I1 plus I2. I1 plus I2 again becomes I and reach the negative plate of the battery, and that will further reach complete the circuit, and that will keep on happening. This is how the current is distributed in the circuit as per the Kirchhoff's current law. Right? Now let's apply the Kirchhoff's voltage law to any of the closed loops. We can apply Kirchhoff's voltage law only to a closed loops. Let me name these points as A, B, C, D. So I can apply Kirchhoff's voltage law. Applying Kirchhoff's voltage law, which says that the sum of the algebraic sum of the voltages in any closed circuit equal to 0 in this loop A, B, D, A. In the loop A, B, D, A, To apply the Kirchhoff's voltage law, first of all, we shall consider either a clockwise or an anti-clockwise direction. Let us consider a clockwise direction. Like this. This is the clockwise direction. And if you remember back the rules, if the current is passing in the same direction of the clockwise that you have chosen, treat that potential drop as negative, otherwise positive. Now look at this P. Current is passing in the P I1 in this direction. Our clockwise direction is also the same. So the potential drop across this P is negative. What's the potential drop formula? IR. So minus I1, resistance of that is equal to P. Now come to this galvanometer. See, this is how the current is passing. In galvanometer also current passing in the same direction. So that potential drop is also negative. Let the current through galvanometer is Ig. Let the resistance of the galvanometer is G. Then it becomes Ig and G. Now come to this place, to this R. Current in the R is passing in this direction, but our clockwise is opposite to that. Therefore, potential drop across that shall be positive. So what is the current is? I2. So it is positive because our considered direction is opposite to the direction of the current flowing. So plus I2 into R equal to 0. That's the algebraic sum of the currents in any closed circuit equal to 0. We shall do the same for the other loop. What is the other loop is? Applying the Kirchhoff's voltage law in the loop. This one, B, C, D, B. Come back to the same point. B, C, D, B. You shall be careful that in the second loop also you shall choose clockwise. In a part of a problem, you cannot choose clockwise, and for the other part of the problem, anti-clockwise. Both of them shall be the same. Now come to this Q. In Q, current is passing this way. Our clockwise direction is also the same. So the potential drop is negative. So minus current is I1 minus Ig. That resistance is equal to Q. Now come to this part, S part. This is the chosen clockwise direction and the current in the resistor S is passing in the opposite direction. So potential drop is positive. So plus I2 plus Ig is the current, like we have explained basing on the Kirchhoff's law. Resistance is S. And come to this point. In the galvanometer is current is passing like this. Our direction is opposite. Therefore, potential drop is positive. Plus Ig into G equal to 0. These are the two equations. Equation number 1 and equation number 2. Now, there is one thing that we need to apply or make sure that the Wheatstone bridge is said to be balanced when current in the galvanometer equal to 0. That means what? Galvanometer shows 0 deflection. That means potential at the point B equal to potential at the point D. See, this is D, this is B. As the potential difference is same, no current is passing through them. In that case, bridge is said to be in a balanced state. So we want to derive a condition when the bridge is in a balanced state, right? How do we get that balance? We will talk later. First, let us say that's the condition. So equation number 1, in balanced state will be, that means when the galvanometer is showing a 0 deflection. In this equation, you have to put Ig equal to 0. When Ig equal to 0, this entire term becomes 0. So the remaining equation will be minus I1P. This is the other equation. Plus I2R equal to 0. So I1P equal to I2R. Let me call this as equation number 3. Now let's write this equation number 2 in balanced state. 2 in balanced state. In balanced state, galvanometer shows 0 deflection, Ig equal to 0. This Ig becomes 0, this Ig becomes 0. So what will be the equation? Minus I1, this Ig becomes 0 and Q is there into Q. Plus I2, this Ig becomes 0, to S is there. This Ig also becomes 0, so equal to 0. So what is the equation will be? I1Q will be I2S. This is equation number 4. So you got equation number 3 and 4. Let us simply divide these two equations. What happens if I divide equation number 3 and 4, right? So by dividing 3 and 4, what happens when you divide 3 and 4? Let's divide. Let me scroll a little up. This is the equation 3. This is the equation 4. So I1P equal to I2R is equation number 3. I1Q equal to I2S is equation number 4. 3 by 4 is by. So I1 gets cancels, I2 gets cancels. Then the conclusion is P by Q equal to R by S. That means if the bridge is in balanced condition, be careful, that is true only when the bridge is in balanced condition. So that means Wheatstone bridge is in balanced condition. That means the potential difference at the other two junctions is 0, or the galvanometer is showing a 0 deflection. In that case, ratios of the resistors that are arranged in the bridge PQRS are such a way that P by Q equal to R by S. So the law is useful in such a way that if you know two resistors P and Q, you can calculate the ratio of the other two. Or if you know any 3 resistors out of the 4, by substituting them in this formula, I can get the value of the 4th resistance. That's how we can use Wheatstone bridge, which is used Kirchhoff laws. Therefore, it's a direct application of the Kirchhoff law. So it's a conclusion. Therefore, we can use directly rather than going through the entire Kirchhoff law process again and again. That's it. Thank you for watching.